Now let's look at the noise performance of AM with envelope detection. This is with a peak detector. We have the same setup as we've had with the other forms of modulation. The AM signal, again, has an amplitude AC, and then this term in brackets, 1 plus m times x of t. M, again, is the index of modulation, times cosine 2 pi fct. M, the index of modulation, has got to be less than or equal to 1, and we're taking the absolute value of the message signal to lie between, or the magnitude to lie between -1 and +1. And we have the additive noise that has been passed through the bandpass filter. So we have the received signal is the AM signal plus the additive noise. The input signal power is exactly the same as we worked out with synchronous detection, and the input noise power is the same as we worked out with synchronous detection. So we have the same expression for the signal to noise ratio at the input of the demodulator. Now we're looking at amplitude modulation with an envelope detector or a peak detector. So that's going to be a rectifier followed by a low pass filter followed by a DC block. The received signal is the AM signal plus the narrowband noise. So using the narrowband noise model, the total received signal is the AM signal in the first part, plus the second part are the two narrowband noise terms. If we represent the received signal as a phasor, we have a phasor for the AM signal itself, AC times in brackets 1 plus m times x of t. That lies along the real axis in phase. And at the tip of this AM phasor, we are adding the random noise, which is broken down into the in-phase component that points in the same direction as the AM phasor, and the quadrature phase component, which points at 90 degrees to the AM phasor. The AM signal represented by this horizontal phasor, and on the tip of this phasor, we're adding the random noise, so that when you do that, total phasor, when you add all three of them up together, will fall somewhere inside a circle here, but the amplitude and the angle of this phasor will be randomly changing as directed by this random noise added to the phasor. What the rectifier will do is measure the magnitude of this resultant, of this received phasor R of t. This envelope detection, that is the peak detector followed by the low pass filter, that measures the magnitude of this total phasor. And the magnitude of this total phasor is the square root of, we have the real part squared, AC plus AC m x of t, that's simply this first term distributed together, plus NC of t, that all squared is the real part squared, plus the imaginary part squared, which is in the quadrature component in S of t squared, and then we take the square root. The magnitude of this phasor will be a function of time. If we take the amplitude AC, C squared, to be much larger than n sub s squared, and I'm looking at this expression for the magnitude of the phasor. So if AC squared is very large compared to NS squared, then in this square root term, we take this thing that has an AC squared in it, and that's large compared to NS squared. So we're going to first take the case. We can approximate this by taking NS to be very small, so it approaches 0. And we'll look at what's left from this square root term. So if AC is very large compared to NS, then the output of that square root term is simply going to be AC plus AC mx of t plus NC of t. This will all be passed by the low pass filter, and the DC block will eliminate this constant term AC. so that the output signal is going to be AC M X of t plus NC of t. And this, if you compare with the AM with synchronous detection, this is exactly the same term as we had with synchronous detection. The output power is going to be AC squared M squared XT squared. That needs to be time averaged. The output noise power, just as we worked it out before, is 2 times N naught times B. So the output signal to noise ratio is the top of the fraction is the output signal power, the bottom is the output noise power. And this is exactly the same expression we got for synchronous detection. So for large signal to noise ratios, a peak detector performs as well as synchronous detection. So the advantage is peak detectors are much more simple to build and much less expensive than synchronous detection. And if you have a large signal to noise ratio, that is to say, if you're relatively close to the transmitter, if you're thinking about conventional AM radio, then the peak detector works perfectly well compared to synchronous detection. It works as well as, or approximately as well as. So, for example, if we consider tone modulation, where the message signal is a cosine at a particular frequency, and the message signal power is 1/2 the amplitude squared, so that's simply 1/2 times 1 squared. The signal to noise ratio works out to be, we have the expression for the signal to noise ratio, except we're substituting a 1/2 for the signal power, and that simplifies to AC squared M squared divided by 4 times N naught times B. And the signal to noise ratio at the output of the peak detector compared to the signal to noise ratio at the input is going to be 2M squared divided by 2 plus M squared. At most, or at best, M is equal to 1. So signal to noise ratio at the output compared to the input is 2/3. So at best, the signal to noise ratio of the signal plus the noise is worse at the output than it is at the input. It's 2/3. The signal to noise ratio at the output is 2/3 the signal to noise ratio at the input. So that accounts for the inevitable static in the AM signal, AM reception. Now let's consider the situation where the noise is not very small compared to the carrier. So we're not going to ignore this term NS squared. So if we look, this is now the output, or the result of the rectifier. We're finding the magnitude of this this resultant vector, which is going to be the square root of the in-phase components all squared plus the quadrature component squared. When we square the in-phase components, we get an AC squared term, then a 2AC mx of t, and then a 2AC NC of t, and then we have an AC squared m squared x of t plus a 2AC mx of t NC of t plus NC squared. So 1, 2, 3, 4, 5, 6 terms. These first 6 terms come from squaring everything inside these square brackets, and then we have finally NS squared of t. So this is the total signal, and then we take the square root. This will give us the magnitude of this phasor. Now there are several different components inside this total. We have I've done a bit of algebra and combined some terms. This first term under the square root sign, that corresponds to signal. This is the AM signal squared. The term in front of the cosine squared anyway. This the next term, 2AC times NC of t, this has a noise component the NC component, and that's modulating the carrier. So here we are modulating the carrier with the by multiplying it by the noise modulated carrier. This is a real problem because this just looks like another amplitude modulated signal added to our desired signal. So that really steps on the signal. The third term is noise that is multiplied by the signal. This is signal dependent noise. This is a problem as well, which says that even if we up the power in the message signal, that's going to drag in additional noise. So that is a problem. And then the last term is the additive noise, which we can't do anything about. But these two middle terms, the noise modulated carrier and the signal dependent noise, that just adds a great deal of noise to the resulting demodulated signal. So if you think about lightning, which is a very short duration current pulse, which would induce electromagnetic waves in the through space. This produces a large pulse of noise, and that would then modulate the carrier, and it would also be drug in additionally by the signal itself, and but mostly since it modulates the carrier, an AM radio turns out to be a very good lightning detector, because every lightning pulse causes the carrier to be modulated, which comes across as a burst of static on AM radio.